In the name of Allah, the Compassionate and the Merciful. Hello guys, my name is Salar Delabar Qashqai, and in this video we're going to model Gable frame and then having a optimization and sensitivity analysis. You see that, guys, in this picture we have one Gable frame, and this Gable frame has 4 non-prismatic elements, and with 200 nodes and 600 degree of freedom and 196 discrete prismatic elements. So the elements, for example, column 1 start from I to J, beam 1 started from I to J, and also column 2 start from I to J, and beam 2 start from I to J. And we applied the distributed load at the top of this beam 1 and beam 2, and in node 150 we have incremental displacement, and based on this incremental displacement we're going to output the result of base shear and displacement based on pushover analysis. So you see that, guys, and we use this I section for our definition, and also stress strain relations for these I sections fiber for material properties. And you see that, guys, if we run this optimization problem with the demand moment at the base of this column in node 1, so after let's see in here, after 6 iterations we get the solutions with 348 section 2 web height. So this section is going to optimize with 348 millimeters. So let's back to the OpenSees file. You see that, guys, in here as an optimization problem. We use Newton-raphson for calculating this process. We defined many functions to plotting and outputting the data, and in here we defined a pushover analysis function. So in this we defined column web height and other properties, for example H1, H2 and L1 for definition of these properties, H1, H2 and L1. So the structure is symmetric, so all the properties from the left side equals to the right side. Okay, guys, and you see we defined material properties, and also we defined column 1 and column 2 and beam 1 and beam 2 properties for sections, and defining the each nodes. You see that, guys? For example, we use this formula for calculating the each section's web height and then defining the fiber sections elements. And you see for beam 2 we have this process also, and also for column 2 we have the same process, and then for beam 2 is the same, and then in each definition of the nodes we are going to define the elements, nonlinear beam column elements, and then trying to output the data as a displacement and base reactions, and also trying to define in here the uniform distributed load for beam 1 and beam 2, and then in here trying to run the analysis with the incremental displacement, and so we use different methods and algorithms for this calculation. And then in here we're going to have a non-prismatic I-section web height of this Gable frame optimization. So we defined the properties of this Gable frame, for example H1 and H2, and column sections properties, beam section properties, and number of nodes. So we have 200 nodes, and also in 150 as a node number we are going to apply the incremental displacement. So let's back in here. So we have 200 nodes, and in this position as a node number 150 we're going to have an incremental displacement, and we define the weight, so you can use it or omit this weight for your analysis. And uniform distributed load is going to be defined, and then we are going to use the initial guess of I-section web height for the column. So we use this value as a x, and then defining the Newton-raphson methods for this calculations process, and defining the maximum pushover analysis as the incremental displacement, as we defined 300, and then defining the target base moment as this value, and then the address of this outputted data. And you see that, guys, if we start this analysis, which we did it before for Newton-raphson method, you see that, guys, after 23 minutes we get the solutions with the 3 iterations, and the result with the optimum section 2 web height equals to 348 millimeters. So if in here you're going to plot the elements, column length and web height of this analysis result as a linear relations, you see that, guys, at the bottom of the column 1 we have this web height, and at the top of the column 1 we have this web height. And in here we're going to have the last pushover analysis result. You see that, guys? Our last pushover analysis result has this curve, and based on base shear, degree of freedom number 1, and displacement 448. So we are going to bilinear curve fitted, and you can calculate the elastic stiffness, plastic stiffness as a elastic, plastic, this curve, and then tangent stiffness as a this curve, and then section ductility ratio and overstrain factors also is going to be calculated. And you see that, guys, in this process we can have a very good optimization problem with the demand moment definition. So for example, in here you can change the analysis code and define, for example, demand ductility ratio, demand overstrain factor, or other parameters which you want to calculate and find optimum solutions for this process. So let's back to the sensitivity analysis. So we do the same process and all the process is the same. So we defined in here column, we're going to change actually the, let's see in here. We're going to change the top of the column 1 web height and beginning of web height of beam 1, and then with this definition running 150 iterations as a pushover analysis and then outputting the data. After running 150 analyzing of this pushover analysis, so we have 150 outputted data as a base outputted and displacement, and then trying to using the other parameters for calculations of this sensitivity analysis. You see that, guys? For example, in here we have a column with height from 280 to 75 as a minimum and maximum with a uniform distributed function. And in here, for example, beam section web height we defined from 80 to 150. So based on these two parameters as random numbers, we are going to calculate all the parameters such as overstrain factors, ductility ratios, plastic structural stiffness, elastic ones, so and finding the relations with linear relations between two parameters such as column section web height and maximum displacement. And so you see in here linear relations between beam section web height and maximum displacement of degree of freedom 448. So it shows that linear good fitted, and also other parameters such as to finding the relations between two parameters and finding the R squared. And you see in here we use the correlations of all outputted data, and you see that in here correlations between maximum base shear and maximum displacement has good fitted together. So we must omit one of these values for our futures calculations for outputting and finding the best solutions for these relations between each parameters. So in the code I use the multiplier regression, and based on these multiplier regressions I omitted the base moment base shear, and then trying to find the best fitted linear relations between these parameters. So let's back to the sensitivity analysis. All the process is the same, all the functions is the same, and you see that, guys, in each analysis you're going to calculate the different base shear and moment and then trying to output it. So we defined it NAD, and then we defining minimum and maximum for column section web height, and as a minimum and maximum for these values as a beam section web height, and then trying to run the 150 calculations. If you run this code, you see that it takes near to 7 hours, and then trying to use the outputted data and plotting in here, and in here we are going to multiply regression calculations for best fitted linear relations between all the parameters. So you see that, guys, in this optimization and sensitivity analysis of this Gable frame, we can model very complex structures and finding the best solutions. Thanks, guys. Please have a comment and tell me know about this kind of modeling. Bye.